So let's calculate the mass of S, where S is a sphere, radius 3 with the given density. Very nice applicable example. You have a ball in your hands, and you know density of that ball, and you know how big it is. You measure the circumference, for example, figure out the diameter. From diameter, you figure out the radius. And the density can be measured as a function z squared. Z squared. Here's the picture. Let's first describe this object using any tool we know. As you can see, parametrization is not given. Well, what?
It's a sphere.
It's a sphere. So spherical coordinates. Wow, what a surprise. Will be the best one. And then we know that the radius is 3. Let's write down right away. Let's not do too many steps here and write down that R depends on U and V. U is going to be chosen as theta and V as phi is. And then you remember the formula radius. So let me maybe write down. Radius is fixed. It's not a parameter 3. And then we have x. Remember, maybe if you don't remember, write down like so. X is 3 cosine theta sine phi, comma. Y is 3 sine theta sine phi. And then z was the only one that has 3 cosine phi. Yeah. Again, I always encourage people, I could memorize it, you can memorize it too. And in general, when we give you a scratch paper on the final exam, we tell you put away everything. We give you a scratch paper, write this down really fast. That is legal, that is not cheating. We give you paper, write down all the formulas until you remember them, and now you feel safe. I've always been doing that when I was a student. It's from my head, so it's not cheating, right? So, what is my theta and phi? It seems like there's no restrictions, like we don't have any firsts or whatever octant. So from 0 to 2 pi and from 0 to pi. This is my parametrization of the sphere. This is what something we just learned, but it seems like very intuitively correct. We just used the parametrization, we used coordinates we knew before to describe the object. Now the new formula shows up. The new formula says that the integral they ask us to do looks like this. Like this. Maybe I should copy it to repeat it again. So we will do the first step in yellow part. Let's find the cross product RU, RV. RU, RV are partial derivatives of whatever we just wrote. U is theta, V is phi. Okay, that's a lot, but fine, whatever. So let's do step 2. That was step 1, figure out the parametrization. Parametrization. Step 2, let's do the part in yellow, which is this part. Let's figure out ds. ds is r derivative with respect to theta, cross product r derivative with respect to phi. And then for that, we kind of already have this example before. We did it last time, so I don't want to spend too much time on that. So see before, because we did exactly the same parametrization with we differentiated everything. Now you just need to not to forget to create to find the magnitude of that, which is 3 squared sine phi equals 9 sine phi. Magnitude is, remember that you factor out something, sine square plus cosine square gives you 1, so sometimes it's a very nice number. And finally you build this integral. The integral is 3. So this step number 2 is the longest one. This one has 3 steps, right? 3 steps. Step 1, partial derivatives. Find r theta and r phi. Step 2, you actually find the cross product of these. Step 3, you find the magnitude. So this is a long step. 2 is a long step actually. Lots of work here. Now you're building the integral. The integral by the formula is f ds is integral over df with new parametrization times this cross product, the magnitude of the cross product of the partial derivatives du dv. F is the function they gave us. In this case, it was called density. In this case, it says, oh, it's actually a density of the sphere. So the ball you're holding has a density z squared. For you to understand, it means it's changing. Density was not fixed there. Just like your lungs, for example, they have different density, different locations. And that's why physiology is such a complicated science, because you try to model it mathematically, but it keeps changing everywhere. So it's dynamic, actually. And the dynamical equations are very hard. Partial differential equations. Let's see. It's going to be z squared ds. That is the formula, over s. That will be a double integral. At the very end, d theta, d phi. So that will describe the limits of integration. D phi we agreed from 0 to pi. D theta from 0 to 2 pi. A complete spin around and from north to south pole. The function is given as z. Z have to be changed as well, but we do know how to change z. It was over here, x, y, and z. So it was smart of me to sign each part. X, y, and z. Z is 3 cosine phi. So it's going to be 3 cosine phi squared. 9 cosine phi squared times, and now this piece at the very end, the tail, 9 sine phi. The tail goes here, 9 sine phi. 81 can be kicked out, and you have, first of all, interesting, there is no function in terms of theta. Let's see that first. There is no function inside in terms of theta. It's just integral in terms of phi. So what will this integral from 0 to 2 pi d theta gonna give you right away? 2 pi. Do you remember you integrate going to be theta from 2 pi to 0 gives you 2 pi. So that gives you the answer right away. And you only end up to have an integral 81, integral from 0 to pi, cosine squared phi sine phi d phi. That's a single integral. How do you integrate that? Who remembers?
U substitution.
U sub. How do you choose U?
Cosine.
Yes. Thank you. Good job. It's going to be U. Then this will be minus du and so on. So it's going to be u cubed over 3. U is cosine, so it will be cosine cubed over 3. Add up together 108 pi. 108 pi. And this is one of the applications. So we found how heavy S is, where S is a sphere with the given radius and the given density. That's how you know it. So there's a 3D function z squared, which is representing a fourth dimension. Maybe I should kind of explain this part. This is a 3-dimensional object. It's a sphere. We're describing it with 2 variables, theta and phi. But it's filled in with some kind of liquid and it's shaking. So the density is not fixed. The density is not something you find in a table at the end of the physics book, as I remember. The density is changing as z squared. So it's a 4th dimension, and that is why this function is a 4th dimensional function.
Like a water balloon?
Yes, it's like a water balloon. Very good idea. So it's a 4-dimensional object, and that's why we need upper dimensional calculus to find things like mass of the object with the given density, which you need to learn how to describe mathematically. And that's why it's called surface integrals. Yes. Yeah.
So when we convert it to spherical coordinates, normally there was that tail, like the rho squared. So what happened to that tail in this?
Yeah, good question. That was triple integral thing. Since we don't do triple, that completely disappeared. That's one of the old ways to do it as well. She's asking, remember there was a triple integral that was rho sine phi d rho d phi d theta. Triple integral also had applications using density. You can find the mass and so on. So we're jumping away from that to one more way. And that's the confusing part, that there's so many methods to do different things, different dimensions, but it still seems like this is 3-dimensional thing with the mass F over here. Same idea. And here we're describing a ball, which is 3-dimensional object, And now we're using a set surface integral, and we get the same result. So that's interesting that we just do it different ways, but we decrease number of integrals here, which makes it easier to calculate. And instead, we're using this idea of approximation, this idea that there can be a surface below and a surface above, and we're trying to find the volume of the solid under the function f and over the given surface. In this case, because sphere is such a popular example, it kind of exactly matches really well the spherical coordinates idea. Good question. You see, you notice that there is a connection between these two. Yeah, that was good. And finally, the last topic is this orientation of the surfaces, and that is taking us to something amazing. What is happening when we try to find surface integrals of the vector field? And we're going back to the very beginning of the class, again, vectors and vector fields. A vector field and a surface S, we want to sum up all the values of f over S. Think like you're collecting all the vectors, f on S. So now, you're not just running on the trail and then collecting all the wind. You are also running on some kind of shape which is changing.
Magic carpet.
Magic carpet, I guess. That's an interesting example. I was thinking of this like there is some kind of, on the water they put some kind of moving thing and you need to run on it. And it keeps moving while you're running on it.
Oh, you're talking about that little surface where you can actually walk on.
Yeah, that's kind of interesting because it keeps changing and you're still collecting the vector field on the way. Is it helping you or not? So how to figure out that? Before, for line integrals, we dotted f with the tangent vector r prime. Dotted means dot product, right? Like so. We did that before. But this time we dot f with the normal vector instead. And it's an unusual idea that we use normal this time. Normal is being created with the formula cross product of partial derivatives. Remember? R sub u and R sub v. You're doing it right now in your homework. So it's coming from these two, gives you the dot product. And there's a f. F is a vector field. The vector field f. So some kind of changing wind is blowing into your face or behind you or inside you and perpendicular to you. To describe this integral, we need this new formula. So it's not new, but we kind of changing it slowly to do the line integral. Compare with what we had before. This is your exam 2 and 3, right? We had this idea. Now we are going to use ds instead. ds will be changed into dot product with a vector of a vector field f, vector field, and normal. Normal is a cross product of partial derivatives. So this tail now is different. To be honest, it kind of makes sense. We used to have one-dimensional t here. So r used to depend only on t. Now r depends on u and v. So now instead of dt, we have du dv, and that's why the number of dimensions increased. Now there's a cross product involved. That is why it's more complicated, because we're doing different parametrization. In both cases, you dot f with something that involves derivatives. That's true. It used to be derivative, one-dimensional derivative. Now it's partial derivatives du dv. Applications. Maybe you heard this phrase from the physics class. Did you? Tell me if you did. Net flux. Have you heard about net flux before? You will actually. It's a very popular thing, especially if you work with physics, electromagnetic fields, or even blood flow. Net flux also describes the blood flow in the body. So mass physiology actually is a fascinating subject to learn. Very hard. I was trying to do it for my PhD and I switched to epidemiology because mass physiology is very, very hard. You need to know some anatomy, biology, physics, binding and unbinding things, and dispersion and sugar dissolved in the blood, whatever. And it's just complicated. It's very hard. So net flux is there as well. Net flux is, let's see, in physics, this integral is called the net flux of f across S, measures how much f flows in or out of S. That's exactly when your heart is opening and closing, how much blood is going in and out, your lungs, breathing in, breathing out. The cell in general opens and closes, how the cell interacts between each other. So that is very popular in physiology, biology in general, and of course magnetic fields, how they switch on, switch off. So the heart example is a good one. So it measures how much F flows in or out of S. So if it goes in and out, now the direction matters, and that is pretty cool. So the blood coming, the air from my lungs coming out is not the same as coming in. That means that the integral will actually show the direction now, and that is pretty fascinating. Not you just running around now and collecting the wind and saying, oh, the wind was helping me, so the integral is positive. This time it actually will calculate how much went in and how much went out. And that means that the direction of the surface matters now. That takes us to the Mobius strip slowly. So let's see. Let's do the example, and that might explain it a little bit. Write down this example: double integral f ds over s, where s is a helicoid parametrized by. Luckily, we have parametrization. On the exam, if you see parametrization, instead of freaking out like you probably will, you should be happy. This saves you like half an hour, because you're supposed to do it yourself. I'm just trying to tell you. If you see I gave you parametrization and it says parametrized by, boom, you're supposed to sit there, smile, and I'll be like, wow, that's weird. But yeah, it's rare when people smile during final exam. But no wonder. That's a new phrase I learned. No wonder. I like it. Yeah. No, the people ask us, where are you from? And we're from Arizona. Of course they meant, I'm from Ukraine or not. And I'm from Arizona. And she looks at me like, no wonder. Like, what did she mean? So now I really like this joke. No wonder. This is how it looks like. It's basically a spiral helicoid. Or it's helix, right? Going 3D, and it has those little arrows are surface, direction of the surface, going out. So let's see, how did we decide on that and what is going on. So try to sketch a pretty picture if you can. Some of you are very artistic. I definitely have high respect. I saw some of your drawings. It's really impressive. For others, just good luck. Or pay money to those who can, and they will make a bigger picture. I actually should have, you did not remind me to sync.
Personal artist. Professor, for the final, were the U's and V's be more distinctly different?
Are you again? Seriously? What is your problem, Jacob? U, V.
Yeah, is it look like that, or does it look like the text of a V? U, V. I don't know what to say. No, they will be exactly like this.
Well, no. Here's a point. One's like the bottom of a smiley face, and one's like.
Yeah, I see. No, it will be exactly like this. It's already coded, so no, I will not gonna recode Microsoft Word for you. That's not how life works.
You can just print one right on.
So, step 1. Let's sketch the picture. This is my look at it. I'm so talented. Such amazing picture. And then step 2. Let's find our slopes. Our slopes are partial derivatives. That's the step I skipped before. I said we did it before, so it's not very interesting to do it again. But this time, let's do it. It's a new function, not spherical anymore. Let's find partial derivatives. Since we are given the parametrization, that's very convenient. But as you can see, it's a very classical parametrization. It's kind of r cosine theta and r sine theta and r. That's exactly what helix is. R sine and R cosine is a circle in 2D, and then Z, it's keep growing, so it's keep going up and down forever. Not forever, it's actually fixed like so, from 0 to 2 pi. Let's find partial derivatives. Differentiate with respect to U will be cosine V, comma sine V, and 0. Since last one doesn't have any U, it's just 0. With respect to V, it will be minus U sine V, comma U cosine V, and then V gives you 1. That's step 2. Step 2 is the longest one because now we need to find the normal vector. Normal vector comes from the cross product. Remember, cross product used to be your biggest problem. Now it's kind of intermediate step, to be honest. And we hope you do it fast, and it's not the biggest problem anymore. Step 3, we find a normal. Normal, n. N is the cross product of those partial derivatives. Do you remember why? Can anyone remind me why? Maybe explain better than I do. This like particular phrase. Why n is the cross product of those partial derivatives? Do you remember why? Or are you just memorizing the formula? Because I think it's easier to just know why. Anyone? Yes? Yeah?
I think so. So when you take the partial derivative with respect to u, it's like finding the slope along your surface
Yeah.
with respect to u.
Yeah.
And then with respect to v, that's the other direction, same thing.
Yeah.
The slope with respect to v. And when you cross product, it's always perpendicular to those two vectors.
Yes.
The normal vector.
Exactly, thank you. And u or v are lying on the tangent plane. What is perpendicular to tangent plane? Normal plane. So normal vector is a cross product of these two. I think it's easier to know how it's getting, where it's getting from than memorizing it. So I was wondering if you understand this. Thank you. Normal, let's do it, and then you remember how to do it. I, J, K. And then we put cosine v and sine v and 0 minus u sine v. Make more space, not like I just did. Move a little bit, nice. U cosine v and 1. And then you multiply everything you multiply the way it should be. Collected terms. Skipping this. Sine v minus, no, not minus, it should be a vector. Remember, cross product is the vector. Cross product gives you, that's why we call it vector product. Векторное произведение, that's how you call it in Russian. Vector product.
Yeah.
That makes so much more sense now.
I agree.
Right? Молодец. Yes. So this is the vector, which is n. This is a sticking away vector from the tangent plane, perpendicular tangent plane. Finally, you build the integral. Step 4. Integral. Integral is surface integral f is all this vector field floating in the air, maybe magnetic field stretching you from all sides below and above. But now you do it while you are on a surface. You're not running the treadmill anymore. You're like everywhere in 3D, while this thing is also everywhere in 3D, and you're collecting those arrows while you are on that thing. The formula is going to be double integral over d f times, and the tail. Since f now described with respect to parameter r used to be in terms of t, not anymore. Now r in terms of u and v, and that's how you should memorize it. Now, because of that, we're using this cross product, which is normal. We just found it, like so, du dv. Also, as you can see, we don't do magnitude anymore. Magnitude was for the previous examples when there was no collecting arrows. When you collect arrows, it means we're talking about vector field. No magnitude is needed. That is a difference. Before, it was a finite number, which was like a mass of the ball. That one had a square root. This one does not. This one is actually a dot product with the cross product. So that's how hard the material became at the very end, that it collects everything we learned before, which is double integral. That will be du dv at the very end. Du dv, right? And then we know which one is which. V is given from 0 to pi. Check the beginning, it told us this. U is from 0 to 1. And you have f. F is 2u cosine v, comma, 2u sine v, comma, v squared, times the tail. We just calculated it. Sine v minus cosine v u. That is the tail. See, I'm not consistent putting parentheses with sine and cosine because international people did not agree, actually. Do you have to put parentheses inside of the sine or cosine or not?
Yes.
Okay, if Jacob says, then we should probably we should do that. So you multiply everything carefully. This is dot product. Remember how to do dot product? You component by component. Component by component, and then v squared times u, blah, 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 and it will simplify very nicely, which is a good thing. And now you add up, dot product is a scalar product, so you add up together everything. And it simplifies really well, because 2u cosine v times sine v minus 2u sine v times cosine v cancels out. So you only have v squared u left. V squared u, double double du dv, from 0 to pi, from 0 to 1. Integrate that. Those are two different integrals, actually. You can break it into that. And you have pi cube over 6. So this number tells you information about, for example, the magnetic field. Wasn't stretching you, shifting you somewhere, or maybe it did not even reflect anything on you. So the picture is like so. You was running on that thing, which is called helicoid, which was parametrized with u and v. F. Have you ever asked me how did we get f with cosine and sine? You always remember, if this is given, then this is automatically x, this is automatically y, and this is automatically z. So we plugged in x, y, and z right now in the integral. Did you notice? U cosine v, u sine v, and v. We plugged it in. And that's how you completely rewrote the integral. F was rewritten in terms of parametrization as well.
Professor?
Yes.
In the graph, could that represent like a propeller moving?
Yeah, definitely. Now, aerodynamics is all involving line integrals there. That's why it's so amazing. So, interesting point to say that orientation matters. Make sure that n is a cross product, points upwards for graphs and outside, right? For closed surfaces like spheres. So people just agree what n points to, and if you want the other direction, you do minus n. That's what people do. N should point up for surfaces, upwards, and not inside for up for graphs, and not inside for spheres. Inside will be negative. So it makes sense. It's positive, then it means it's stretching you away. If it's gravitational forces, they're stretching you away. If it's like a black hole, that's a pretty rare behavior. So to go in, we'll put negative n. And in general, n is sticking outside, right? And here's the plane. This is how we create n in the first place. So normal n, that's a pun actually, right? Normal n, funny, points out versus pointing in. Oh, I learned a new pun. I should tell you later, on Friday. I'm not good with puns, so I know like 3, and I learned one more recently.
During the quiz?
I will tell you later. So, rule of thumb, usually but not always, check that the z component is positive. But usually the picture tells you how to do it. Let's do one more with net flux now, with this one. This is also a sphere, but in the first octant, so that's why the picture is like that. Let's calculate net flux. Again, net flux calculates how much things is going in and how much things is going out. The blood flow, if you think about it, the air in your lungs. What is the physical applications you can think about? I don't know. It goes in and goes out. Oh, electromagnetical probably. Ions come in, come out, right?
Yeah.
Yes. Across the given surface, S is a sphere, but we decide to use only in the first octant with radius 1. R is 1. This is how it looks like. So it's a sphere, but we only need it in first octant. Here it is. That one is easy to sketch, I think. We have used the same parametrization. Let me know if it's too fast.
Can I see a problem?
Yeah. I'm afraid maybe I'm going too fast.
Thank you.
Here it is. For now, I can tell you the pun. Okay, we'll see if you like it. I learned the pun. It's hard to memorize puns because it's in English kind of joke. So if you put a root beer into a square cup, you just end up with beer. Right? I'm telling you,
I like that, man.
I can die now.
right? So that's my like number 4 plan I memorized and was able to recreate it by myself. So.
What I'm understanding is, if you're underage, you can still get beer.
Root beer?
Root beer is not
Not
alcoholic, yeah.
Put it in a square cup.
Yes, so that's the idea. You put it in a square, it becomes beer.
It's not magic.
It's math magic.
It's beer, I swear.
So do we recognize this parametrization? Yes, we do. R sine cosine, R sine sine, R cosine, but R is 1. So just let you know, it's not R did not disappear. It's 1. And it's not R, by the way, it's rho if you remember, but doesn't matter. And now we're restricting theta to be from 0 to pi over 2 and phi from 0 to pi over 2 because we're in the first octant. That's down the restriction. We're finding the normal vector. We did it before. It's exactly the same idea. But we need to make sure that, what did it say? Net flux. If we're choosing it to go inwards, not outwards, we have to use minus n, and that is a difference. So the original one is given like so. This is what we had from the previous examples. We're working with this field like 3rd time already. So it's the same equations, the same differentiation comes here, the same cross product. Cross product gives you a vector, remember that. And the last one ended up to be negative. The last one tells you that if it's negative, usually, it's not all the time, but it has a note here, usually, but not always, z should be positive to have a normal sticking out direction. So the blood goes outside of the heart. That's the normal n. If you want the blood to go inside of the heart when it's pumping in, then it should be negative. So since this one is negative, we have to change n to be completely the opposite side. So this z kind of showed us that since it's negative, because of that, we can see that we actually want to see how much blood goes inside of the heart. Thus, you're choosing as a modeler, mathematician, or physicist, or engineer, but not a computer scientist. I like making jokes of computer scientists. Computer scientists don't do that because computer just knows what to do for them. You choose minus n, and then you change all the signs because of that. Let me stay here for a second. I will zoom out for you to kind of comprehend what I just said. And then we will be almost done. Just 10 minutes left. But the idea is, it's a little bit too much to comprehend in the last week, and that's why I think we need at least 1 or 2 weeks for this material to like it. Because it's amazing, the idea that the ball has 2 surfaces, and that makes sense, right? When you play with the ball, it has inside and outside. So surface has a direction. Surface is different from outside and inside. Even material is usually different here and there. So your head has different sides, inside and outside. Your hand has different sides, inside of the skin and outside of the skin. So that is interesting that we never actually described it before. In 3 calculuses, we never mentioned that the side of the surface is important because it takes us here, very, very far of the material. Vector fields, normal, cross product, surface integrals. Finally explain this idea that usually we want to see that the direction points away, but if it does point in, then we're going to choose minus n because, just lost my pen, because n goes out, so minus n will go in. That's the idea. It's still normal, as you can see. It's still perpendicular to the tangent, but now it goes to the center. So we're changing the sign, and then you don't have to write this down. I'll just give you the notes. You do the same thing we did before. You multiply f by n. Here's your f converted into the parametrization we chose. N came from the cross product u times v. In this case, it's theta and phi. No magnitude is needed here. Multiply and get a number. So this was the tricky case when we had to switch the orientation, and then the sign changed everything. So let's see. This takes us finally to this famous object, which is called Mobius strip. It's not the only object. There's also, do you know which one? One more object is also famous for that same idea. There are at least two objects which have one surface only. So N changes orientation, meaning that it goes from inside to outside. Usually, let me describe what's the difference. Usually, here's a strip. There's N goes outside at the top, and N goes inside at the bottom. Very simple, and we call it minus N, not to create any new abbreviation. In the Mobius strip, look at it. I'm putting a pencil. It's outside, somehow becomes inside. Goes back, and now goes outside, somehow becomes inside. So N is doing this. Look at that. N is doing this. It has only one side. It's kind of idea that if you... Oh, I actually have it here. Like this kind of rubber band, if you connect it together by flipping one and gluing it, then it will be only one surface. It's exactly like that. So it will be one surface. So you see, if you look at this little crab walking on the strip, it never changes the direction. It just keeps walking, but at some point it's inside and some point it's outside. Do you know why they chose the crab? Because it's not falling, I think. So Mobius strip is definitely fascinating. And the other one is what? Do you know? The bottle. Nobody knows the bottle?
You show us the picture?
Yeah, of course. Yeah, which one?
Klein's bottle, I think?
Yes, Klein's bottle, exactly. I don't remember. It's in English how to write it down. Klein bottle? Yeah, what's the how to write it down?
K-L-E-I-N, I think.
K-L-E-I-N. Yeah, I found it. K-L-E-I-N. I know it's in Russian. Yeah. Here it is. That is this 3D shape. It doesn't exist in real life. Although, you know, you can try to figure out. Here it is. And then I'll find you the animation. The animation describes it even better. And that is pretty fascinating. So with the strip, it's still kind of two-dimensional object in 3D, but this one is three-dimensional object, which does not exist. And that makes it pretty cool. It's also in Futurama, by the way, so you definitely should watch it. See? Let's see if it runs. It's always outside over here, then it goes inside, and it keeps going. Oh, come on.
Oh, there we go.
Yeah, the small one works. Let's see if the big one works. Oh, okay, here it is. See, the green indicates pointing inside, the red pointing outside, but it's never switched. It just does switch by itself. So it's a not existing bottle when you have something inside and something outside all the time.
Oh, it moves.
It just moved, yeah.
So this doesn't exist in real life?
Yeah, you can try to build it.
exist in real life.
You can make it like so. So here it is, but it will not be realistically correct. The people try to do it, so there are some kind of. Here it is. Okay. Here it is, you see? So the piece from outside goes inside, and that's why whatever was outside the surface becomes inside surface. That is there.
How do you drink out of it?
But you don't. It doesn't exist, okay? And not all bottles are made to be drink of, okay? At the first place. No, some of them are for decoration.
You sound like my mom.
Right? Don't touch that, Carlos. That's for guests. So this is a pretty awesome idea, and here
When was that discovered?
we can check, yeah. And there's a joke about this. Why did the chicken cross the Mobius strip to get to the same side? Oh, yeah, look at that. You liked it. I'm glad you liked it. So let's see if it's all I wanted to say or not. So it's interesting. It took us 2 years to get into the idea of Mobius strip, which is actually known thing. And usually people would ask you these questions when you have games. Do you know what Mobius strip is? Usually people do know, but to actually understand the idea of it took us 2 years of learning calculus.
I think we made one of these in elementary. Like,
Right?
Take a piece of paper,
You cut it and flip it. Yes, exactly. Good job, people. I'll see you on Friday.